Hello and welcome. I hope you are having a great day. In this video, we are going to understand loss function, optimization, and gradient descent. Okay, so let's set up the agenda. We'll also understand some nitty-gritty details within them. So we'll start with loss function. So we'll cover the complete life cycle, understanding the loss function and why the loss function needs to be convex. And from there, we will understand optimization, like how loss function relates to optimization. How do we formulate optimization problem? What is optimization about? Then we'll also do constraint optimization, and finally we'll end with gradient descent algorithm, which is used to solve an optimization problem. Okay, so that's the agenda. Lot of topics to cover, but this will give you a complete picture about a basic machine learning linear regression kind of setup. Okay, a regression kind of setup. Okay, let's begin. So first of all, whenever we build any machine model, right, so we want it to make least mistakes in its predictions. Okay, so and these ML models will make mistakes. So how do we measure those mistakes so that we can minimize those mistakes? So we can tune the model so that it minimizes those mistakes. So how do we measure those mistakes? So these mistakes are measured in something called loss function, the loss that the ML model incurred while making the predictions. Okay, so that is called a loss function. Now let me write it down. So this is for loss function. So ML model will make mistakes, and this is a way to quantify the mistake or the error for a single data point. So when we train ML models, so we give them multiple data points so that it can learn something. Whenever we are training machine learning models, we give them lot of data, and each data is different. So each data is a unique data point. Okay, so if we know that what mistake it is making on one data point, and we can somehow quantify that error, okay, then we can cover it up for the complete. We can take an average of over the complete data set, but first the unit is over a single data point. How to quantify that error? So loss function is nothing but how to quantify the error or the mistake made by the model on a single data point. Okay, so that is, it quantifies error made by a model made on a single data point. And for regression, all this I will discuss within the context of regression. Okay, so for example, in regression, what kind of losses we have? We have squared loss. You can square the loss. Whatever is the difference, loss is the difference, right? What it should be, what is the prediction actually, and what the model has made. So we can square that so that the mistakes is even amplified. Okay, we can have squared loss. Then we can have something called, when we read SVM, so we'll have something called hinge loss. You will see that for going forward. Or we can have this absolute also, but we'll see why we don't use and in what cases we use this. So these are like for a single data point, how do we measure them for just one data point? But there will be multiple data points in a data set. So when we take errors for each data point, and when we average them out, we have a special term for that, that is called cost function. It's just good to know stuff. Generally the loss function works for all, but sometimes, okay, you should know this. So cost function is the average loss functions, or average loss or mistake or the error, quantified error. Okay, average of average loss over entire data set. For example, if I'm using a squared loss, that, okay, what is the difference between the predicted and the actual value, or actual and the predicted value, and I just square it up. So that will give me the individual data point loss, single data point loss. And if I take the average of it, then what is it called? It's called mean squared error, MSE, mean squared error. Similarly, we have mean absolute error also. Okay, so these are some kinds of cost functions. And there's one more thing related to them called objective function, which is umbrella term of all those things. What is the objective that you are trying to do? Okay, so just I'm mentioning it, but this loss function is what we will be taking forward, and I will use that interchangeably for cost also. Okay, the loss, this is loss function, and the loss will be the complete cost. Okay, that's how we'll take it forward. Okay, so let's understand it with an example. For example, you have a stock trading bot kind of thing. Okay, algo trading. So it is making predictions for the stock prices, so for any company, so that it makes more money and minimum loss. So for each actual value, so yi, so there is a stock price which is actual value is yi, it makes predictions corresponding to that is yi hat. Okay, so for example, a company's stock price is like rupees 1000, and this is making like rupees 980, something like that. Okay, just some random example to understand. And say this is like, once again it is 1000 only, and now this is making like rupees 1020. So both of them, if you see the difference here, okay, so here if you see difference, okay, error equal to yi minus yi hat. So here you have minus 20, here you have 20, yi minus y hat, and here you have minus 20, right? So if I want to, so y just so like this I will make some, okay, n measurements for n data points. So these are individual data points, like this I'll make it for n. So if I just take a sum of all the entries, so that I can just tell, okay, this is the total error I made, this is the magnitude of total mistake I made. Will that make sense? No, right? You can see in this example itself, because this is plus 20, this is minus 20, and after if you sum up like this, if you have such values, the net for these two transactions, the error mistake is 0 only. That's why just taking a simple sum of the errors is not a good idea. So next you will suggest, why don't you take absolute value? Okay, you just take the magnitude of it. So my you take error as absolute error, that is equal to absolute value of yi minus yi hat. But we have seen in the fundamental calculus class, right, when we are talking about differentiability, that this x bar function, this is not differentiable at x equal to 0. Okay, how is the graph? So generally the graph is, for absolute function, the graph is like this, x equal to y like this, and then this is y equal to x, this is y equal to minus x. Okay, for both, if x is negative, this is y equal to minus x, if x is positive, y is equal to x. This is the graph, and at 0 you see this is not differentiable, and we have seen this because the gradient here is minus 1 and the gradient is for plus 1. So the gradient at this point is not smooth, it is changing from minus 1 to plus 1. Okay, there's a cusp. We have seen this is the limit does not exist at, because the gradient is coming from 0, my negative side is not same as gradient coming from positive side. Check that video for the details, but I've given you enough details to understand. So that's why, and most of my optimization, so when we come down later, gradient descent, etc., they use some form of gradient for in the algorithm to solve, to get the final solution. So that's why this is not a good idea. There is a hack to get around this, but for now let's assume that this is not a good idea. Okay, so what's the next? So that's why we have a squared error. So we have squared loss, a squared error. Okay, so that is like yi minus yi hat square. So even if the loss is positive or negative, the square will be same finally, and plus it will amplify the error. Okay, whatever is the error, right, to amplify it, so the magnitude will be amplified so that we can capture, so bigger losses will be magnified more, that we want to minimize them finally. So that's why square loss is a preferred idea. So I hope this is clear. Also it has more properties. Okay, we'll discuss when we come to the next point, right? So we will understand that why squared loss is preferred, because of this square. We also, you have seen the graph of y equal to x square. This is a parabola, okay, and this is a downward parabola. Okay, it has a minima, so this has a minimum point. So if the loss is formulated in this way, so it has some point where it will be, the loss can be minimized. So we know that if this is formula, this is the curve for y equal to x square. This is also having minima, but this is not differentiable, okay, at 0. So that's why this was invalid. Here also this is y equal to x square, and say you know that y equal to minus x square, right? If take the negative sign, what will be the graph like? If you have y equal to minus x square, what will be the graph look like? So it looks something like this. Sorry. So let's assume this is at 0. Okay, this is your y equal to minus x square. So this is your maxima at 0. So that's why we won't get a minimum. We want to minimize the loss, right? So there will be no point where this function is going to be at a minimum point. This is always at a maximum, and the minimum can go till anywhere. Okay, minus infinity something. That's not a valid. Yeah, that's why we prefer to have a function which will have a minima, which is curving upwards. Okay, and such kind of functions, which brings me to the next point. Before that, so this loss function that we did is we are trying to quantify the error, and this is from data to now we are bringing into the maths, okay, side, so that we can solve it using the maths. We had the data, and now we are trying to, okay, move this data, and this is the link, that loss. And once we have the loss figured out, now we can apply the topic that it will come later. So now we can convert this as an optimization problem, and when I discuss about optimization, then we'll get into more further details of what is optimization. But this loss function is the bridge between data and optimization. So now we have all the information about loss. This is just quantifying the errors, and we have got one suitable. Okay, so we want to find a suitable function which can model this, okay, or formulate this in a mathematical way, so that we can do further mathematical analysis or operations on this. So y equal to x square, this seems to be a good candidate here. Why? So there are some properties, some good to, okay, what should be a good loss function? So what should be a good loss function? So for a good loss function, okay, it should be differentiable. We saw that because the gradient, descent, etc., they use the derivatives, so it should be differentiable at all the points. Plus the second thing is it should be convex. Only then it will have a minima, because we are trying to minimize it here. So it should be a convex function. Okay, so what is convex? Convex means it is curved upwards. Curved upward. So only when a curve is curved upward, only then it will be having some minima point, right? So if it is something like this, only then that will have a point of minima. The value will be here. So that's the reason it should be convex, so that we can get the minimum loss. If I am formulating my loss as a, means I have to minimize the loss. That's how I'm formulating my problem. So these are the two requirements because of the algorithm that I'm using, and then also the that I should come to a minimum point. So these are the reasons. These are the two requirements. Differentiable, we have discussed in detail in the fundamental class. What is the meaning of differentiable? Okay, so let's briefly discuss about convexity here. What is the meaning of convexity? In simple terms, convexity means that, say for example, if a function is convex, then if I draw any line, okay, if I draw any line, say for example, I have, what is the meaning of convexity? Let's pull it up, and I'll draw here only two simple examples. So for example, I have this thing, and I have some curve like this. Okay, and I'll draw one more so that you understand it, so the discussion will become clearer. So I have another function where you have something like this. Okay, so let me make it a bit smooth. So what convexity says theoretically, that if I have any 2 points on the curve, and if I draw a line, if I take any 2 points on the curve and if I draw a line, then it should always be above the curve. Okay, and this fits the bill. But if you see here in this curve, right here, if you have this point and this point, say I'm drawing a line, but is it always above the curve? No, the bottommost point is here, but still I have connected 2 points on the curve which is above the curve. Sorry, it is the below the curve. It is below the curve. So I have got such a point which is below the curve. I have got such a line segment which is below the curve. So this is not convex. So this is convex. Yes, this is not convex. Sorry. So generally, so mathematically speaking, so this is the intuition that any line segment joining any 2 points should always be above the curve. Okay, it should be above the curve, any 2 line. So mathematically, if I give you some formula for here, so the maths would be like that. So convexity for this too, okay, this is always described in terms of convex set. Okay, so there's a concept of convex set. It is described in terms of that. So I will leave the convex set part, but I'll give you one simple thing. So for convexity, that whatever I said, that the line should lie above the curve, right? And mathematically, it's written as if a function maps a n-dimensional vector to a scalar, then for it is convex. Okay, it is convex. This function is convex. Okay, if for all, this is for all symbol. Okay, for all x comma y and theta belongs to 0 comma 1, that is in the interval, theta is belonging in the interval 0 comma 1, this equation holds. So f of, let me be careful, theta x plus 1 minus theta y, this part is less than or equal to theta times fx plus 1 minus theta times fy. So for all xy and theta in the range of 0 to 1, this equation tells me that the any line segment lies above the curve. Lies above the curve, and this says that if this is true, then only we can say that is convex. And plus, it is always described in terms of convex set. I'll not go into the convex set definition. Okay, but this is what this is the equation about this. Okay, and also there's one more test. So there is a second order test of you can do. So there is a second order derivative test. Second order always when I say it, so this is second order derivative test. So second order derivative, as soon as we have multiple variables, then what comes to your mind? Multivariable and then second degree derivatives. So it will always be defined in terms of Hessian. This is a second order derivative for multivariate. Whenever multivariate calculus is there, then you will have a Hessian there. So this is defined in terms of, okay. So for that, if the function is twice differentiable, so f is twice differentiable, only then the Hessian will be existing, right? So the function is twice differentiable and second derivative exists. That's what it means. So if the function is twice differentiable and the second derivative exists, only then we can talk about the convexity of it. And f is convex. So this is the requirement, and f is convex. Okay, if and only if, if and only if the Hessian, okay, Hessian is a positive semi-definite. Okay, positive is PSD, positive semi-definite. Let me write full, positive semi-definite. How do we check for positive semi-definite? If there's a semi-definite, then there should be a positive definite also. So I'll just tell you the terms meaning. Okay, so I'll just introduce you to the terms so that you can make a map of it. If we go into the details, it is a lot of detail. Okay, but I'll introduce you to the terms so that you know. Okay, so the Hessian should be positive semi-definite. How do we say that? Positive semi-definite. So for example, I'll give you a quick example for which. So if fx is equal to x square, then your second derivative, your Hessian will be equal to second derivative del square f by, so just write del square f, this delta will suffice. So it will be equal to 2, which is greater than 0. Okay, this implies this is a convex function. So this should be positive, means greater than or equal to 0. Positive semi-definite means greater than or equal to 0. So how the so this is written as PSD, positive semi-definite. So there is something called positive definite also. So what is the test for positive definite? Hessian. So a Hessian is said to be positive definite if, so there are two ways to test this. So one thing is the all eigenvalues of Hessian are all eigenvalues. I'm talking in terms of Hessian. Okay, so I'm talking about Hessian. All eigenvalues of Hessian lambda I are greater than 0. So all of them are positive, not even equal to 0. Okay, so what does Hessian measure? The Hessian is measuring the second derivative, right? So it is measuring the curvature. Okay, it is measuring the curvature around that particular point. Okay, so if it is so this will give me, so if it is all positive means the function, okay, the function is curving upwards in all the dimensions. So a function that will be multiple dimensions, it will be, right, a function, because this is with multivariate, the function there can be multiple dimension, x1 x2 till xn. So if all the eigenvalues are positive, this means that my function is curving upwards in all the dimensions, x1 x2 till xn. Okay, so that is one test. And then there is a second test for a non-zero vector z. It is positive definite if z transpose is absolutely greater than 0. Okay, this is a non-zero vector z. For this, if this is greater than 0, this implies it is PD. The Hessian is PD, and this H is your Hessian. Okay, these are the mathematical rules. These are coming from, if you want to revise here, then you can go and revise all the matrix calculus that we have done. What does it mean? Okay, this is a positive definite. I'll put the link of that video in description. Okay, if it is not. So this means that this is a convex function, and the function is increasing in all directions. Okay, this means the point is minima. Here the point, this is curvature is going upwards, the curve is going upwards in all directions. That's why this point is minima. That's what positive definite means. But the requirement is that it should be positive semi-definite. Even that will suffice. So what is positive semi-definite? It is just, so it is in terms of Hessian only again. So the first condition, that all eigenvalues, so eigenvalues lambda I can be greater than or equal to 0. And second thing is, again, for a non-zero eigenvector, so this z transpose can be greater than or equal to 0 for a non-zero vector. What does this mean? That, so here we said that if all the eigenvalues are positive, okay, and this is also holding, means the second condition, either of this will work. So the for each dimension, x1 x2 xd dimension, if it is there, right, so in each dimension the function is curving upwards. But here some of the eigenvalues can be 0 and some of the directions can be 0, means it is not strictly convex. Not strictly convex means in some directions it is curving upwards, and some directions wherever the lambda value, sorry, if these lambdas are 0, right, they will be flat. Okay, so they are not strictly convex in all directions. They can be flat in some directions, and that's okay. Flat in some directions. So directions means all the this is in multiple. That's why linear algebra is important. Okay, so this is in, it can be, a vector can be in multiple dimensions. So in some dimensions it can be flat, that is fine, and at least we have the function is convex in some directions. Okay, that's what it means. So finally you have understood that we need a convex function for a minima, for the loss function, which, because we are trying to minimize, so we need a minima point, and I want it to be convex, and this ensures that there will be only one global minima. There will be only one global minima, convexity, and that's why we can just take the algorithm and just reach to that global minima. Whatever algorithm is there, we can just, like gradient descent, we can just reach to that global minima. Okay, so now we have formulated our problem loss function, and we have found that it should be differentiable and should be convex. Only then I can reach to the minima point and I can get there. So now let's try to find the ways to reach. How do we formulate this problem? At what point will I hit the minima? And for this, what is the next point is your optimization. So we reach to our optimization in calculus. So optimization is a way to find, it's a way to find a best solution. Optimization, you are finding like maxima or minima, right? So it is a best solution from the alternatives you have, from the set of alternatives. That is your optimum. These are the options available from set of alternatives, and which is, for example, this is a y equal to x square, right? So these are all the points available. So at which point will it be minimum? So that's why I want to find. So that will be my best solution. That is my optimum. So that's why it is called optima. These points are maxima, minima are also called optima. And reaching or finding for what values of x will I reach that maxima, minima point or the optima point. It can be maxima or minima both. That's the best solution. It can be both direction. But here in our case it is loss. We have formulated it as minima. So in our case I'll talk about minima. Okay. So that's what optimization does. So where we have the loss, which is mostly a minima problem. So you want to find the optimum parameters such that we reach that, means the this loss is minimized for the machine learning model. That's what you want. Find a best solution from the set of alternatives. So now, formally, if you say what it is, formally if you define, this is a optimization is an iterative process. Iterative process, okay, iteratively, okay, to find the parameters, to find parameters, okay, like for example, if it is one variable, then x star, that, or w star, the weights, okay, that minimize the loss function. So you defined our loss function that it should be differentiable and to be convex, so that I can reach a global minima, and I will know that this is the minimum loss that I can incur using this model. The way we have means not using the model, the way we have formulated the loss function. In our case, it was mean squared error. I'll take that mean squared error only and we'll move forward. Okay, so x, so we can write, so instead of w square, if I write it in terms of x square, x star, so this x star is the optima, point of optima. We have to find this x star will be the minimum arg-min we write. So this is the minimum the argument for which my fx will be minimized. So the value of x, for example, if I write this, draw this like this. So this is my y equal to, is your y is equal to x square, right? This is your, and we can say this is your fx also. F of x is equal to y. So my fx is x square. So I want to find that argument x which will minimize my fx. So that will be your x equal to 0. So here in this case x star will be 0. And how do we find that? So we'll find, so simply if it is one dimensional, then no problem. This is a 2-dimensional, right? This is 2-dimensional, no problem. But imagine this is in n dimensions. then how will you solve? So this is just for the 2D. All these 2D visualizations are there to understand the concept, but we are dealing with n dimensions here because there will be n dimensional features, okay, in machine learning models. So x star will be 0. We know that. Why? Because we have seen this so many times. So optimization problem is to minimize the loss. My optimization problem is to minimize the loss. So we have formalized this loss function as a optimization problem now to minimize loss. How will we write this mathematically? So we'll write that. So if it is a model now, so minimize, okay, find such weights w comma w naught. W naught is the bias, okay. These all terms will get clear, but I'm just introducing you to these terms. So these are the weights or just the coefficients in each dimension, okay. And this is the initial, this is the bias for the model, okay. And this will be equal to, so we'll minimize the average 1 by n, I equal to 1 to n, and the mean squared error yi minus yi hat square. And for minimizing this, we want to find such weights where this distance is minimum, the actual and the predicted, they become, so we want that should be very close to each other, should be very close to, only then this will be minimized. So we have to find such weights that these two come very close to each other ideally. So this is the parameters of the model. So this is what I hope the optimization link is clear. Optimization, what is optimization? So out of all the possible parameters, there can be multiple values of x, right? So these are all the alternatives. So these can be all the alternatives. From that I have to find the value of x that will give me the best solution in case of your minimizing. So this is the best point where x will be minimum. And for x equal to 0, y will be minimum. I want to minimize y, right? This is my fx. That's the task. So for that, that is the out of all the possible values of x, x equal to 0 is the optimum or the best solution. That's what it means. It is iteratively we reach there. We find that x star, here x star will be 0 in this case. We can see this visually also. And mathematically also you can just do a quick differentiation and you can find out. So we'll do a simple another problem. So we have formulated a loss function. We have taken a loss function. We have formulated as a optimization problem. We want to find the best parameters which minimizes my function. Okay, best parameters that minimize my function. This is my loss function, and now I want to minimize this, and this is your optimization problem to find the best solution. So for example, I'll give you a simple example now. So that this x square, I'll just make it a bit complicated. Fx is equal to x square minus 4x plus 5. See, this is the equation. It is not simple x square. So what will be your f dash? So first derivative, this is to check whether it has an optima or not. So it will be 2x minus 4. Okay. So if we equate this to 0, what will be my x star equal to here? This will be equal to 2. X star will be equal to 2. This is the point of optima. This is the optima problem. Optima point. Not problem. This is optima, point of optima. It can be either maxima or minima. And how do we test that? We take the second derivative. Second derivative is equal to 2x minus 4. This is just 2, which is greater than 0. This means that x star equal to 2 is a point of minima. Here the function will be minima. F of x will be minimum at this point. If this is not clear, we have discussed maxima minima at in detail in my fundamentals, calculus fundamentals video. I'll put the link of that video in the description. Okay. So this is there. So now we understand what is optimization. But always the optimization problems may not be, okay. So just the variable, we have to find the parameters given the condition, okay. It may not be such simple problem. In real world, there can be so many limitations or constraints when we have this problem. So we can have many, so we cannot choose from all the options, all the alternatives available. There can be some limitations that you have to find. Say for example, if I give you a limitation that you have to find the minimum value between 1 and 2, I limit the range of x, okay, here that x can be only between 1 and 2. So if I give this constraint, will my x star be equal to 0 now? No, because this is the constraint I have applied. Now I cannot even consider this. So my x can be only between 1 and 2. So now I'll choose x equal to 1. That will be my next new optima. Only because I have limited. This is the constraint that I have put, that I can have x only in the range of 1 to 2. Okay. So this is the meaning of constraint. I'll give you few more example, a concrete example that will make it amply clear. We'll solve this together. But this is what we understand by the meaning of constraints. So this is an optimization, and there can be some constraints on this, and that is called constrained optimization. Okay, in real world we can have constrained optimization, for example. Okay, so what is the meaning of? So I cannot choose the min or max from the complete set. Okay, but there with a, so I have some set of limitations. These are some set of limitations or constraints imposed on optimization. So now the set of possible solutions has reduced because of these constraints. Anything constraints confine our options, right? So I'm trying to find the best possible solutions, and if I have some constraints, then I have to choose within those constraints. That's what these constraints mean. And even in our real world problem, we will have constraints. So given those constraints, what is the best possible solution? So that is what is your constrained optimization. Optimization is always trying to find the best solution. And now constraint is like, given these constraints, find the best solution now. Simple. So these constraints can be in two forms. So whatever, so in the mathematical format, so either these constraints can be of equality, that something should be equal to something. Say for example, if I have a function g of x is equal to c, given a constraint, so I have to minimize fx. Or there can be inequality, like h of x is equal to d, no, not equal to, greater than or equal to d, or just greater than d. Both works. So now we can say that so I have to say that, say if I say minimize f of x subject to the constraints. What are the constraints? That g of x is equal to c, that is the first constraint, and the second constraint is h of x is greater than or equal to d. So I have to somehow include this also in my minimization problem. Okay, these are the constraints that are required to be satisfied. Without this, my solution won't be a correct solution. That's what these are the constraints: equality constraint and inequality constraint. So there are multiple ways to solve this, and one of the ways which is popular and we will keep on using in machine learning, and I want you to introduce that. So all this purpose is to introduce you to the terms and the methods that we are going to use in our machine learning module. Okay, so there is a method called Lagrangian method. Okay, Lagrangian method to solve this constraint optimization. So what Lagrangian method gives me is, okay, so what does it give me? So it gives me, it adds a Lagrangian function. Okay, it adds a Lagrangian multiplier, which converts this constrained optimization into a unconstrained optimization. So it adds a Lagrangian multiplier that converts my constrained optimization to unconstrained. Unconstrained, we know, right? You have to just minimize for these kind of problems. So just minimize this, no constraints, nothing here. Only one function we have to minimize. So we will just take a derivative as we took here. Equate it to 0, find the minima, and check for the second derivative. That's how we go. Generally, we just equate it to 0, assuming that because this is a convex function, so that will be a 0. But all the times we cannot take the derivative, so there are other methods to do this. So what is it? So let me show you an example. What do I mean? For example, so this will become, next problem. So after I've converted this into using a Lagrangian multiplier. So my loss function, this is given as loss function. Where is it? So this is given by L. L is equal to your loss function. This is given by your capital L. Okay, so this L is used in different terms in different ways. So here also it will be, now L of, earlier it was L was a function of X only, and here I have to find, now my L will be a function of a Lagrangian multiplier. This lambda is your Lagrangian multiplier, and now this will be equal to, for example, if I have equality constraint f of x minus lambda times g of x minus c. Okay, so g of x was equal to c. I'll bring all of them on one side so that it becomes g of x minus c equal to 0. Multiply it with lambda and just add it here, minus or plus, whatever works. Okay, generally this is minus. Okay, so we have now two parameters, so now we have to optimize in two parameters. We have x also here, and we have to find a lambda also. For what lambda will this be optimum? So now not only I have to find x star, I have to also find the lambda given. So solving this will give me, so if it was only x, what did we do? We differentiated with respect to x, got an equation, find the optima. Okay, and that would be minima because the function is convex. But now here I'll have to differentiate it with respect to x once, and then also with respect to lambda. Only then I can solve, because I have to get the lambda also now, because only then this is also having the function gx here, right? So now the constraint optimization, this will become minimize x star. So this is my loss function, new loss function with the constraint loss function with lambda Lagrangian. Okay, so this minimize x star f of x minus lambda times g of x minus c. So this is your new optimization problem, optimization, whatever. By solving this, we will get the x star. And how will we solve this? We will have to differentiate it with respect to both lambda and x star. I hope this makes sense. Okay, if not, let's solve a real world problem so that you get the complete hang of it. What am I meaning? So normal optimization you understood, right? I just differentiate it, equate it to 0, and get the point of optima for single. Conceptually it's clear that I have a convex function, so it will always be a minima, and if I blindly differentiate it, equate it to 0, I'll get my point of optima. That will be my x star. That's what we got here. We just checked for the second derivative to confirm that this is a point of minima, because we didn't know whether this is a convex function or not. But generally our loss function should be convex, so we can just equate it to 0 directly to get it. Okay, because the criteria is it is a convex function. So let's see a simple problem so that it makes the concept clear, so that we can use these concepts directly in machine learning. So we have to find a point. So for example, so we have to find a point which is closest to origin. So I have my x and y axis 2D plane. So give me a point which is closest to the origin, right? Your answer will be straightforward, 0, 0. That is the origin, that is the point closest to the origin. Why do I need to find something else? But if I give you another constraint, that this point, find a point which is closest to the origin, which lies on another point, and I'll give you the equation of that line. So now you have to find the nearest point from the origin on that line. So that's the constraint I've imposed. What was the vanilla problem? That if I say find the closest point to the origin, this is a simple optimization problem. Okay, simple optimization, find the best solution from all the alternatives. So I'll just say 0, 0. This is the point closest to origin. But now I'll give you a constraint that find a point which is closest to a point which is on a particular line. I'll give you the equation of that line. And now you will have to solve this constraint using Lagrangian multiplier. So let me write a problem. Find the point closest to origin. Okay, and it should be which is on the line, so I'll give you the equation on the line, say 2x plus 3y equal to 13. Okay, which is closest to the origin on this line. How will you find now? So my function is to minimize, and what is my objective function or the loss function? What will be the objective here? So objective function will be distance from origin. That's what I want to minimize. How do you calculate distance from origin? So for example, if I have a coordinate, if of xy, point xy is there, right? So f xy is there, not f. So if I have a point xy, its distance from origin 0, 0 is given by square root of x square plus y square. So what will be my, I have to minimize the distance, minimize this distance, square root of x square plus y square. So can I write my objective function or the loss function as minimize x square plus y square? So minimize x comma y, x square plus y square. I will simply square it also, no problem. If I just put x equal to 0, y equal to 0, if you differentiate it, it will give you 2x equal to 0 and 2y equal to 0 if you do partial different derivatives with respect to each one. And you can get x equal to 0, y equal to 0, and also the second derivative will be 2 and y, so that will be your point of minimum. That is the minimum distance, no problem. But what is the constraint? The constraint is your, this is your fx, right? And your g, this is your fxy, f of xy. What is the g of xy? This is equal to 2x plus 3y equal to 13. So what do? We make it as gxy is equal to, so this implies 2x plus 3y minus 13 equal to 0. And now we'll make a combined. So now my L of lambda comma x, I have to find x and y also. X and y is equal to x square plus y square, okay, and then minus lambda times gxy, so minus lambda times 2x plus 3y minus 13. This is with your Lagrangian. Okay, so now we have to optimize this. So this is in two variables, single variable was fine. Now this is two variables plus a Lagrangian. So for getting the optima, we will have to differentiate it with respect to each term. So first we'll find dou L by dou x. Okay, so what will be the partial derivative of this with respect to x? Only this has x term, this has no x term, and then this lambda 2x has x term, right? So this will, and we will equate it to 0. This implies 2x minus 2 lambda equal to 0. This implies x equal to lambda. Let this be equation number 1. Similarly, equate dou loss by dou y equal to 0. This implies 2y and then minus this 3y lambda is there, right? So y exists here also. This is 2y, y will become 1, this will be minus 3 lambda, and this will be equal to 0. This implies y is equal to 3 by 2 lambda. This is your equation number 2. Keep equation, 3 equations, 3 variables. We'll have to solve it finally. You can also use matrix, but here we'll solve it with hand. And then dou L by dou lambda is equal to 0. This implies x is constant with respect to lambda, y is constant with respect to lambda. Only this lambda terms will be there. So lambda times this is there. So this lambda will be there, and the complete, this will be like a coefficient to lambda. So this complete thing will come. So this implies 2x plus 3y minus 13. This will be minus times minus of this will be equal to 0. So minus anything is 0, 0 only. This implies 2x plus 3y is equal to 13. Okay, that's what it will be. Negative I have removed, and I have removed the negative sign, so this remains, and I have brought 13 to this side. That's what I have done. Simple. Now we know this is our equation number 3. So now let's solve this equation. So now we can put x is equal to lambda in this equation, and y is also I have in terms of lambda. I can put them here and solve it. So let's solve. So this will give me 2 2 lambda, x is lambda, plus 3 into 3 into 3 by 2 lambda equal to 13. This implies lambda common. 2 plus 9 by 2 is equal to 13. This implies lambda is 2 2s are 4 plus 9 by 2, 13. So this is also 13, right? So this 13 and 13 will cancel out. This implies lambda is equal to 2. So we got lambda is equal to 2. So for that constraint, what will be my x? So for x is equal to lambda, this implies x is equal to 2, and y is equal to 3 by 2 lambda. This implies y is equal to 3. So this point x equal to 2 and y equal to 3 will be the point closest to origin given the constraint that this should lie on this line. I hope now constraint optimization is clear. Constraint optimization. If that is clear, then let's move on. So we have seen that now we can formulate a loss function. It should be convex differentiable. Then we move that that this can be finding the minima of the loss function, minimum loss. This can be formulated as a optimization problem. And then now we have to try a way to solve this optimization problem. So now we have formulated a problem out of the use case that we have. That I'm making some predictions. I want to minimize the loss. I have made an optimization problem out of that. And now how do I solve this optimization problem? So there are certain ways to solve these optimization problems, and the ones that we'll discuss here is which are gradient based methods. So we'll discuss ways to solve. So these are ways to solve optimization problem. So we have the optimization problem ready. This was very simple vanilla problem, so no problem, but we are talking about n dimensions. So this was just to show you, this was a toy problem that we discussed now, but we'll talk gradient based methods. Here, gradient based methods. There are other analytical methods also, like a normal equation for linear regression. There are analytical methods also, so note. So there is an analytical method. There are other methods also, but for example, other than gradient based method, there is an analytical method also, which is called normal equation. For example, normal equation of linear regression, where everything is in the matrix form, and then you get optimum W star is equal to, in the form of this vector x transpose x inverse into x transpose y. We'll also derive it in one class. Don't worry. This is simple derivation. It will come from the squared loss itself. From there only will come here. So this is your normal analytical method. We won't discuss this. This gives generally if you plug in the value, and if this matrix is invertible, then we get a direct answer from this. Sometimes the matrix may not be invertible all the time, right? We know. So there are other ways to find pseudo inverse. That's an approximation of that. So those are other days. These discussions are for other day when we dive deeper into linear regression. But for now, we are talking about general calculus that is required. From that, we'll talk about gradient based methods, and the first one in that is gradient descent. This is used everywhere. So this algorithm is used everywhere. So this uses first order methods. So it uses only gradient. So this uses only gradient. And there's another method which is not used directly, but it is used in combination with other algorithm, which is Newton's method. So I won't cover Newton's method in this video. I'll create another video for that. But today we'll discuss gradient descent. So Newton's method, where this uses it is a second. This is first order method, because it uses only first order, means first order derivative, and this is second order derivative method. it uses second order also, and it uses both, okay, both gradients, both gradient, that is first order, and Hessian, which is your second order. Okay, this is del square f, this is your del f. It uses both of it, and we'll see how Hessian makes the convergence to the minima faster. Instead of just going on the first order slope, right? If I go to the second order gradient, it will converge faster to the optima or the mean or the minima. We'll see this in another video. This is a very small thing. We'll discuss quickly. But let's focus on gradient descent first. So how does it use? So what is the gradient descent? So this is the first thing we'll discuss. Machine learning means gradient descent. This is the bread and butter. That's what we keep on doing, gradient descent, gradient descent. So this is the gradient based method, as the name says gradient, because this what does it do? It will iteratively adjust. So we randomly start, adjust the parameters of the model, will initialize randomly, and it will iteratively, okay, adjust the parameters of the model in the direction opposite to the gradient. Only then it will reach the minima, right? Whichever is the direction, it will go opposite to that, okay, and opposite to the gradient. So let me tell you what do I mean. So for example, we'll use the same parabola. This is your parabola, okay. So this is a bit steep, but still okay. And let me write numbers. Say here, this is 1 2 3 4 5, 1 2 3 4 5. This is your x-axis, this is your y, okay, and this is your y is equal to x square. So this is a parabola. Minima is here, and here you have -1, -2, -3, like this, -4, -5, okay. So -3, -4, -5, something like this, 0. So if you see on this side of the curve, y equal to x square, so as x is increasing, y is increasing, right? As x is increasing, y is increasing, so the gradient is also increasing. And if you see on this side, as x is increasing, x will increase always in the right direction, your y is decreasing, so the slope is always negative. It is changing, but it is negative. Here the slope is always positive because it's going in the upper direction. So here the slope is positive, always going in the up, this way, wherever. If you increase x, y will increase. Here, if you increase x, here from here, if y is so high, I increased x, moved in the right direction, increasing is moving in the right direction. So it will decrease. As you move, increase x, y is keeping on decreasing. So this, all the gradients at every point are negative, right? Say for example, if I start from here, okay, if I start from, say, from 3 initial point, x equal to 3, and I'll have a corresponding y, so that will be 9, this point. So now I have to do a gradient descent on this point. So I'll just give an example, and assuming that slope is, there'll be some positive slope because this is slope is positive, okay. On this we have understood this, right? So this slope in this direction is positive. So now what did we say? Adjust the parameter in the direction opposite to the, so we have to find an optimum x. So I'll just talk about the x here. So say I am at x equal to 3, slope is positive. So if I want to find the next parameter, so how it is, x, how do we write it? What is the formula like? So x nu, okay, or the weight nu, okay, we are adjusting the weights like that. Weight nu is equal to weight old plus eta times, this is your learning rate, we'll discuss about this also, minus dou f by dou w at the old weight, okay. I'm explaining you this part, that y moving on the negative side of the gradient will always take you towards the minima. So here the slope is positive, okay, and the old one was, say for example, this is 3, and then this is the rating, this is your eta, whatever is there, and this negative slope, so this is positive, so my negative slope will be opposite to this is always increasing, so I will move on this direction. Okay, so the net slope will, so whatever I'll get, so I'll get a negative value because df by dw is positive here. At this point the rate of change of weight is positive here, so net I will move in this direction. So anyways I'll move in this direction, it will be negative because the slope is positive, so the net will be negative. I'll move towards here. Similarly, if I am at some point here, okay, like -3, -3, and now here the slope is negative because it is decreasing. Okay, so my this point is say -3, and my derivative is slope is negative here, so minus of negative slope. So here I am, so it will add something to it. So for example I will move, so -3 and the slope is negative, so I will add something, so I'll move -3 plus something, so I will move in this direction. This direction means on the slope I'll move in this direction. So in any way I'll move towards my minima, and that's why this negative derivative is important. That's the meaning of the negative. So in one step you are covering both the directions. Either direction you go to this direction or this direction, you will always move towards the 0 only, because the slope is negative. Negative or negative is positive, so you will add -3 some positive. So -3 plus positive, it will become -2, and you will come down. Here it was 3, slope was positive, so negative, so you will move towards the negative slope, and so that's why you move from 3 to 2. So you will subtract from something from 2. Say if this slope is +1, this is -1, so this will become 3 -1 because this is negative. Negative of 1, so this will be 3 -1, and here this is from -3, and this will be negative of -1, so 3 plus 1, so I'll go from -3 to -2. So in any way I will moving towards the optimum or the minima. I hope this is clear. I've spent enough time explaining you. Yes, so this should be clear by now. So this is your formula. This is important. The new weight. So I haven't made you understand the concept this way, but this is about weights. What will be the optimum weight? So we are trying to solve the optimization problem. For that we had earlier this constraint optimization or finding the optimum weights. Where did we put that? This positive semi-definite. This one is our loss function. Okay, so I'm trying to find the optimum weights using gradient descent. Now this was just an example. This is the loss function for our initial stock trading problem. So this is my loss is a squared loss, so that is the So let me write the algorithm officially. What is it? So whatever I have discussed, I will just make a note of it. So what is the algorithm? Step 1, start randomly, initialize weights with some random value. Initialize, there is also ways to initialize this, but I am telling initialize weights with random values. Okay, step number 1. Step number 2, calculate the gradient at that point. So whatever is the weight, okay, calculate the gradient at that point. We want the gradient, only that's the only variable. Calculate gradient of loss function or cost function, sorry. Okay, so the L or I'll use interchangeably. This is cost, that is average of all the losses individual. Okay, cost function at current parameter value, whatever is the parameter, because this will be iterative parameter value, that is your old weight. Okay, and the third one is update parameter. Okay, how will you update the parameter? Using this formula. And then you have got this. So you want, first step is initialize random weight, so that you will start with some weight, and then you will calculate the this, instead of f I'll write loss to make it loss function. Okay, so calculate the gradient of the loss function at that point, and then you get this, and then update the parameter. So now your new parameter will be the old parameter, and which way. So old parameter was, say for example 3, and now you old weight was 3. So depending upon this slope, you will get the new weights, which will take you towards this minimum. You will adjust the weight because the slope is positive here, so you will go towards the minimum. You will go down, so your weights will be updated such that you will move towards the bottom of the valley. And then what is, and then the next, repeat steps 2 and 3 until convergence, that is until you reach the point of minima. And what is your learning rate? So this is also, so what is your learning rate? It's also an important parameter which can be tuned. So here, say for example, learning rate is nothing but the steps that you take. Okay, say for example, I'm calculating my weight. I have some weight I have at this point. Okay, I have calculated a new weight. So if my eta is big, okay, very big, so I can jump from here to here directly. I'm multiplying it with that value, right? So some very big, say eta is 1000. So I'll directly jump here. Then I can directly jump this side also. Then again I calculate, I'll come here. Then again calculate here, and then like this I can come here. So if my eta is very big, okay, I can keep on jumping like this, and finally I'll come here. Or I can have a small steps. I can go slowly, like this, and then finally I will reach here. Or I can jump here, and then after some time it will come here. So this learning rate is nothing but the step size that I will take. I will take big steps, or I'll take small steps. This you have to find out by tuning, hyperparameter tuning. Okay, so what will be a good so this you have to find by trial and error. What will be a good learning rate for my model? Okay, generally we start by 0.01. That works for most of the cases. Okay, so that's what is your learning rate. Learning rate is the step size. Step size to take for each parameter update. Where will my next step be? So this is your learning rate. Okay, so now if this is clear, gradient descent, learning rate, all this, everything, the algorithm is clear. Now let's move to the types of gradient descent, which is important. So what are the types of gradient descent? So there are 3 types of gradient descent that are popular. So first one is that batch gradient descent, then there's stochastic gradient descent or a random gradient descent, and the third one is mini batch gradient descent. So I'll go with the first one first, batch gradient descent. It's called BGD short form. Okay, batch gradient descent. So what happens here? So now you have to, so the only difference in all these 3 algorithms is that how many, so I will have n data points in my data set. So there'll be a big data set, there'll be n data points, right? So how many of the data point I'm using for calculating this gradient? That's what is the only difference. So this is divided on the basis of number of data points I'm using for each parameter update. So all these types of gradient descent are based on number of data points we use for calculating the gradient for each parameter update. So that's the only basis on which all are different. So how many data points I'm taking at once? So batch means the complete batch. If I have n data points, I'm taking all the data points at once, and for every parameter update, I will take all the points to calculate the gradient. That's what it means. Batch means complete data set, all the batch, complete batch. Okay, so it completes. So this means that it will use complete data set. Okay, in each iteration, for each parameter update in each iteration. So every iteration we are iterating, right? Update. This is the algorithm. So for each iteration, for calculating this, it will use all the parameters, all the points, complete data set. That's the thing. Say for example, if I give you an example, so my loss function. So I have a loss function small li. Okay, this is your individual loss function is for individual data point loss. This is equal to yi minus yi hat whole square. Okay, and say if I say li for weight w, this is for all the weights. Okay, so this is for all the weights. So this is only for one data point if li is this. So and I have the complete loss is equal to average of all these individual data points for the complete data set. So I will sum from 1 to n, and I will take this yi minus y. So I will take individual losses and I'll sum them up. This yi minus y was for one loss, and I sum them up for all losses. So instead of writing yi minus y hat, I'm writing the loss for individual data point. So my loss of w, this I can write as loss of w, L of w. This is a function of w now. Okay, this is equal to 1 by n sigma I equal to 1 to n li of w. And what will be my dou loss by dou w? I'll have to differentiate this. 1 by n sigma I equal to 1 to n. It will be dou li of w by dou w. So this is what I want to calculate for each iteration. That's what I want to calculate, right? So what does this mean? For each iteration, I'll be calculating the loss for each data point, and I'll take the average of it. For each data point, I will calculate yi minus y square, and I'll take the derivative with respect to the weights, and I'll take the average, and this value will be used for updating my parameters. So my new parameter will be based on all the points, the average of loss of all the points. This is for one point, this is the loss, and this will be the rate of, this is the loss, and the derivative of the loss with respect to weight for one data point, and this is the average of all. Okay, so how do we write? So this means your w new is equal to w old. Now I'll bring the minus outside. I'll write minus eta times average of, I'm writing it in words, all n gradients for all the loss. What are the points that you need to understand? So if I'm taking all the points, so my time complexity will be of order of n for each iteration. I'm talking about each iteration, so it will take all the endpoints. So this is very slow. Okay, these are slow steps. But finally, since I'm taking all the data points into account, so gradually, even if it's slow, it will smoothly, it will come down the value, the gradient here, which is the, but it comes down smoothly because it's taking into account all the points. So it will smoothly come down here and settle down here. Okay, so finally we'll converge. Okay, so it will be a smooth and direct path to minima. So I'll reach the minima smoothly and directly there, and the number of steps that way is minimized. To reach the minima, the number of steps is minimized. Okay, but for practical purposes and modern deep learning, this is impractical, because in one data set you can have millions or even billions of data points. So if I go and take the derivative for each point for the loss, okay, I calculate the loss for each data point, and I take the derivative with respect to weight for all the million points, this is practically impossible. So that's why for modern deep learning, where the data set is very big, millions and billions of data points, we don't use this. That doesn't make practical sense. So there is another way that we do. So the second way is Stochastic is nothing but random. It's a word for random. Stochastic gradient descent. So it's called SGD. What do we do here? So what did I say? That is only the way, okay, the number of data points that I'm choosing for calculating the gradient, loss of the gradient of the loss. So here I'm just choosing randomly one data point for calculating. So it uses one data point randomly for calculating the loss in each iteration. So the idea is that it will randomly pick one data point out of your n data points. It will randomly pick one data point and it will calculate the loss and the derivative of the loss with respect to the weight, and it will proceed. Okay, say for example, if I have dou loss of w by dou w, so this will be approximately equal to 1. What was the loss of one data point? So only one. So there we had average of all the data points. This one, here we have only, so this is for with respect to only one data point. Say for example, say I is equal to 5th data point out of, say, if I have thousands of data points, so I'm taking the 5th data point randomly, and next time I'll take some other data point. So this is how you start updating your weight. So your new weight will be, so W new is equal to W old minus eta times gradient of loss at data point I is equal to 5. Okay, so whatever is calculated at data point I equal to 5, so that's what will be my new data point. So what are the points to remember around this? So this is what will be the time complexity. This will be order of 1 because I'm just taking one point randomly. So this will be very fast, no problem, no doubt about that. This will be fast. Okay, faster than the complete batch which is taking all the things. But this, I'm randomly picking points and calculating the gradient, right? So I will not move smoothly down. Batch was I was getting all the picture, the complete picture of the data. I was smoothly moving down. But here I will just move randomly. Okay, so here I can just move randomly here, then randomly here, again randomly here, then randomly here. Like that it will keep on. So that's really very noisy. Okay, but it will converge, but it will be very noisy. So we take hacks that as soon as we reach near the optima, right? So we reduce the learning rate so that it doesn't keep on jumping. So as we reach near the optima, we reduce the learning rate. So it means the step size, we reduce it so that it slowly converges to the optima or the minima point. So we do some hacks around this. This is faster, but very highly noisy and zigzag path to optima. Okay, so high variance in the gradient. Okay, so because there will be high variance at each point, so this will make the path very zigzag. Okay, and the hack which I said that we can use, you can reduce the learning rate when it reaches the optima or the minima point so that it converges and it stays at that point. Otherwise it will keep on jumping here and there if you have big steps. Okay, we reduce the learning rate. So this is called learning rate decay. There are algorithms for that also. I won't go into that, but I have given you the idea. And the third one is there. So there is a third one which is called mini batch gradient descent. MBGD. Okay, so this is your mini batch. So this is generally, okay, this is generally called SGD in terms of deep learning, right? So in DL, this is also referred to as SGD only, stochastic. But the main point is, this is just a good thing to know. But the main point is that this was too slow. Batch gradient descent was too slow as it was taking all the points. This is fast. This is taking one data point, but it is going in a very zigzag way. So it will go very slow for convergence. So I have to take a path which is middle, which takes into account the goods from both, and somehow it manages the middle path, and that is what it is doing, the mini batch. So I won't take all the data points. I will take a smaller subset, but I won't take just one data point. One data point is very small. It will give you some random noise. So I will take the middle path, not one, not all, but something in the middle that will be very small and manageable by the computer. I won't process all the millions of data points at once. Okay. So I take the middle path and I will do use small randomly selected subsets of data point, subsets of data set only. All right. So I'll use small data set subsets. Okay. This is called a mini batch. This is called a mini batch, not a complete batch, but a mini batch, a small batch. Okay. And here the size. Okay. This is greater than, say, the size is k, and this is less than n. So we have a size which is greater than 1 but less than k. So generally the size, okay, so it ranges from 32 to 512, and this will be in power of 2 mostly, because all these batches are matrices. Means this data points are matrix or vector of some form. So we send all this for processing on GPUs, and there, for that reason, we take it as power of 2, because vectorization becomes easy. So we convert this into vectors, these data points, and move it to GPUs for parallel processing. So all the data points, all the batches can be processed in parallel. That's why this is in powers of 2, 2 to the power 5, 2 to the power 10, like that. That's the reason. So this is the minimum, and this is the, typically this is the range. Depending upon the problem, you can move to different size of batches also. So how will my loss look like now? So loss of weight is equal to, now I have, instead of averaging all, I have over 1 to k data points, and this will be small l, right? So I will take average of the k data points, the subset. Say for example, I am taking my k is equal to 32, the lowest. So I will take a subset of 32 data points, and I'll take the average of the loss, and then I will use that as my update parameter. So my W new will be equal to W old minus eta times the average gradient of loss for k equal to 32 data points. So this will be the new parameter update in each iteration. So it is a middle path between the random stochastic, which has only one data point, and the bulky batch, which uses all the data points. And this is what it's used in all the deep learning algorithm. So what will be its so similarly, let's see the characterizations. So the time complexity will be order of k now, which will be definitely less than order of n. So this is moderate. So the speed is moderate now, not too fast, not too slow, moderate. And the second thing is, it is less noisy. So I'm taking the middle path, less noisy than SGD, and then it is faster than complete batch gradient descent, right? More efficient and faster than the batch. And this is the standard technique that is used in deep learning, mini batch gradient descent. That's what you will see. Okay, and then we do vectorization of this because of the power of 2, and move it to GPUs for parallel processing. All the GPUs can process all this data in parallel, and all these batches can be processed in parallel, and that's what gives the speed. Okay, so we have covered all the topics. Let's quickly do a revision. What did we do? So this is a bulk of all the linear regression round. So all the linear regression will be formulated like this only. That's why I have covered it in this way. Linear or any kind of regression problem. So this will give you a backbone or a structure to formulate any problem. So we start with, because your ML model makes mistakes. Okay, so to quantify those mistakes, to quantify those errors, we have a loss function. So depending upon the loss function, okay, so we have a loss function, and the average of all the loss function is called cost function, but we use loss function only for the terminology. Okay, and then we saw that we need the loss function to be differentiable and convex, so that we have only one global minima. convexity ensures that it has one global minima and we can reach there. The deep learning algorithms, okay, they are not, so the deep learning losses, right, they are not convex, so they are highly, so they have multiple uh, local minima, not a global minima. So they may be somewhere like this, and then again there will be something like this. So deep learning is not convex. All these losses are not convex in deep learning. So any local minima also, if we reach, that is good enough. So we don't reach a global minima. So in deep learning, convexity is not a requirement, but for linear regression, etc., so convexity is required. So we understood what is convexity, which is that if I draw a line touching 2 points, then it should be always above the curve. If I draw any line connecting 2 points on the curve, then it should always be above the curve. This is what is convexity. And then we saw that how if I have a loss function and if I want to minimize that loss, any minimization maximization problem is like to find a best solution, and that can be formulated as an optimization problem. And then we saw that optimizations can have constraints, and then we can formulate this constraint as using Lagrangian multipliers, and we can make this constraint as unconstrained. Now I can have all of them in one formula itself, and we can solve this as an unconstrained optimization. We can differentiate it with respect to lambda and whatever is the weight also, and equate it to 0 to get the optimums, x star, w star, whatever we are calculating, the argmin. Okay, so we get these, and then we so now we have a problem, optimization problem at hand. How do we solve it? So there are analytical methods where we directly take a, okay, you use the matrix method where we get the inverse and we solve it, or there are other, the two which are most common in machine learning are the gradient based, and the most common is gradient descent. Okay, in that we discussed batch gradient descent, stochastic gradient descent, and mini batch. Batch uses all the data points, stochastic uses only one data point, and mini batch is a compromise between these two, which uses a subset of the data points. 1 is less than k is less than n. Okay, and there's one more gradient based optimization algorithm which is called Newton's method, that will be covered in the next video. Okay, I hope this helps. So this is a comprehensive coverage of all the concepts that will be required for with respect to calculus for machine learning. Okay, on that note, let's end this video. Thanks for watching this video. Have a good day and bye for now.